Hello again, and welcome to the third introductory video to radioactivity. So in the last video we talked about what is radioactivity, and in the video before that, the very first video, we talked about basic nuclear physics. Okay, so now it is time to talk about ionizing radiation, which is something we're particularly interested in when we think about the security relevant aspects of radioactive materials. So, all naturally occurring radioactive nuclei emit radiation, and they do this in three main ways. They emit a combination of alpha, beta, and gamma radiation. In this video, I will talk about what alpha, beta, and gamma radiation are, and I'll give you some idea of their different physical characteristics. Okay. The important thing about all of these different types of radiation is that they're all ionizing. And if you think back to the first video, this means that these types of radiation can produce ions. That is, they can knock electrons out of the orbits of other elements, thus making those elements radioactive or charged. And in the next video, I'll do a little demonstration that shows how this happens and why it's important. Okay, so let's look at the process of alpha decay. So have a look at the equation in the center of the slide. Here we've got an element X that decays by alpha emission to element Y. So this is represented in the equation using atomic notation. Okay. So the element X goes to element Y plus an alpha particle. So we have the parent X, the daughter Y, and the alpha particle being emitted as well. The alpha particle consists of 2 protons and 2 neutrons, so that's 4 nucleons in total. Let's see what effect the alpha decay has on the mass number A and the atomic number Z. Okay, so because 4 nucleons are being emitted as a result of alpha decay, the mass number A decreases by 4. Okay. Conversely, the alpha particle contains 2 protons. This means that during the process of alpha decay, the atomic number Z decreases by 2 because 2 protons have disappeared from the daughter nucleus. So this shows how a radioactive decay chain is formed through alpha radiation. And I have given you an example at the bottom, if you have a look at the slide. Here we have polonium-210. This is the radionuclide that was used to poison Litvinenko again. It's a favorite example of mine, it seems. So initially this has 210 nucleons in its atomic nucleus, 84 of which are protons. After alpha decay, the 210 nucleons are reduced by 4 to 206, and the 84 protons are reduced by 2 to 82. So the unique element that contains 82 protons in its atomic nucleus is lead, and that's what I've written down here in the equation. So polonium-210 decays via alpha emission to lead-206. Okay, so this is an example of a very nice and simple alpha radiation decay chain. And I've also included a little screenshot of the relevant part of the periodic table there for you as well. Okay, let's now have a look at beta radiation. So beta radiation is different from alpha radiation. If you have a look at the slide, you can see in the top right hand corner that beta radiation consists solely of an electron. So when we use the term beta particle, all we're talking about is an electron. So this is the emission of radiation is the emission of particles from the atomic nucleus. But as you will recall from the very first video, there are no electrons in the atomic nucleus. These instead orbit around the outside of the nucleus. So where does this electron come from? On the right hand side of the slide, you can see the process whereby this comes about. So one of the neutrons turns into a proton plus an electron. Okay, so this is very important because it means that in the process of beta decay, the number of protons in the atomic nucleus increases by 1 while the total number of nucleons stays the same. And this is what I've written down in the form of an equation in the middle of the slide if you have a look. So here I've represented as an equation the element X decaying to the element Y via the emission of beta radiation. How does this happen? Well, as I said, the total number of nucleons in the atomic nucleus stays the same. So although the relative number of protons and neutrons changes, their total number is identical. But what happens to the number of protons, the atomic number Z? During the process of beta radiation, Z increases by 1. Okay? And this is how a different daughter nucleus is formed compared with the parent. I've included at the bottom of the slide an example of how this happens. So here I've included, or rather I'm using as an example, the element represented by K. If you have a look at the periodic table, you'll see that that is potassium. Okay, so what happens here? Potassium-40, which is contained in the human body and also in bananas, contains 40 nucleons, 19 of which are protons. During the process of beta decay, the number of nucleons in total stays the same, but an additional proton is formed from a neutron with the emission of a beta particle. So what new element does this produce? If you have a look at the slide, potassium-40 decays to calcium-40. Okay. So this is a nice example that's relevant to everyday life, given we all consume plenty of bananas. Okay, now, what about gamma radiation, the final type of the 3 ionizing radiations I'll talk about today? If you have a look at the slide, you'll see in the top right-hand corner that gamma radiation doesn't appear to be a particle at all. So unlike alpha and beta radiation, gamma radiation isn't easily describable as one of the 3 subatomic particles we talked about in the introductory slide. So it's neither a combination of protons, neutrons, or electrons. Indeed, gamma radiation is a high-energy photon, a particle of light that is emitted from the atomic nucleus. So unlike alpha and beta radiation, gamma radiation in general does not occur by itself. It occurs as a byproduct of alpha or beta radiation. And I've shown this using a picture on the slide. Here you can see represented in a slightly different way the radioactive decay of cobalt-60, which contains 60 nucleons in its atomic nucleus, 27 of which are protons. So here, what you can see is that cobalt-60 undergoes beta decay. So it decays via the emission of beta particles. But this leaves the atomic nucleus in a slightly excited state. And in order to get rid of the excess energy associated with this excited state, the atomic nucleus emits a little bit of extra energy in the form of light. So a little light particle, a high energy photon there. The final product of this radioactive decay is then nickel-60, which is a radioactive isotope of nickel. Now, gamma radiation doesn't itself produce any changes in either the mass number or the atomic number because it's a byproduct of alpha and beta radiation. Okay, so let's return to the decay chain that we had a look at on the very first slide of this video. Have a look at the slide. Here you can see that at the top we've got lead-212. So lead containing 212 nucleons in its atomic nucleus, 82 of which are protons. So lead-212 undergoes a combination of alpha and beta radiation as a way of achieving a more stable final resting place, I suppose. Now, if you have a look at the chain, you can see this process underway. So this is quite a simple process. For some elements, there are many, many, many more steps that are represented here. Okay, so lead-212 firstly undergoes beta decay. So it spits out a little beta particle. This leaves the total number of nucleons in the atomic nucleus the same, but it increases the number of protons by 1, from 82 to 83. So the unique element with 83 protons is bismuth. So the first step in the decay chain for lead-212 is to transform into bismuth-212. Okay, and then if you have a look at the picture again, you can see that there are now two options. The bismuth-212 can undergo alpha decay, whereby it becomes thallium-208, or it can undergo beta decay, whereby it becomes polonium-212, polonium being our old favourite there. Supposing the bismuth undergoes alpha decay to thallium, we can see that the total number of nucleons decreases from 212 to 208 because the alpha particle consists of 2 protons and 2 neutrons. So that's a decrease by 4. We can see that the atomic number decreases from 83 down to 81 because 2 protons have been removed in that alpha particle. Okay? And then following that decay chain on the left, all the way down to the final resting point, the stable end point of this decay process, we can see that the thallium-208 undergoes a beta decay, which increases the number of protons by 1, but leaves the number of nucleons overall the same. And lead-212's final resting place is the nice, stable, non-radioactive isotope lead-208. Okay. So now we should have enough background to understand alpha and beta radiation and their occasional byproduct, gamma radiation. But let's talk a little bit about the physical characteristics of these different radiations. So you have a look at the slide. There is a picture that represents the various penetrative properties of alpha, beta and gamma radiation respectively. So as I mentioned earlier, alpha radiation is significantly bigger and bulkier than the other 2 forms of radiation. So although it's very, very small and it's invisible to the naked eye, it is quite large by the standards of radiation. And because of its size and because of the fact that it is a charged helium ion, it likes to interact with matter, which means that it tends to be absorbed quite quickly. So here we can see that the alpha radiation won't penetrate through paper, it will be absorbed. Conversely, beta and gamma radiation will quite easily pass through paper without interacting too much with matter. However, the beta radiation is charged. As you'll recall, it's an electron with generally with charge -1, and although it's quite small, it will still interact with some matter if that matter is dense and thick enough. So for example, beta radiation can be stopped by a sheet of aluminium as shown in the picture. Conversely, gamma radiation is tiny. It has no mass. It is just a high energy particle of light, which means that it easily passes through paper, it easily passes through aluminium and glass and other things like this. The only sorts of things that will stop gamma radiation are nice thick quantities of lead, which will absorb the gamma radiation and stop it in its path.